configurations, conformations, constitutional, and of course, the one word we all know and hate, chirality. What the fuck? Okay. So let's just start with a very simple diagram that just goes over all of these vocab words. And that's literally all this video is going to be. Because guess what? Our teachers don't know how to do that. They just don't. I don't make the rules. So let's just start. All right. First up on this really cool list of vocab is chirality. Yeah, we're going to define this one first because I'm going to be using it a lot. And hold up, let me see how to spell it. I don't want to have to define it every time. So get your notepads out, get your iPad Pro, and please write this down. Chirality just means that they are mirror images. And no matter how much you rotate, they don't match up. Like you're on Tinder and you keep trying to get one person, but guess what? You're never going to match up. I don't know what that references. So let's just start with an example. Let's say we've got, I think the example they gave were hands, but we'll start with hands, then we'll use a molecule. Got one hand here. I'm gonna copy, paste, switch it over. Another hand here. And let's change the color. Let's change the color. This one red. I hope to God you know what symmetry is, because guess what? These guys are symmetry. They are symmetrical. Very cool. Okay, mirror images, check. Mirror images just means symmetrical. Please, I hope you know that. Now the part that they don't match up. This part, I get it. It might be kind of hard to understand. What does that even mean? It just means that no matter how much you rotate this little red guy, it's never gonna fit the blue guy. See, you just keep rotating it. They're never gonna be the same. I hate to break it to you, no matter what. And you can actually kind of demonstrate this with a molecule. So let's say we've got our center here. It's very mostly illustrated with a tetrahedral. All right. So instead of atoms and stuff, let's just go with colors. Got plenty of colors to go around. Go with some colors. All right, here is our atom. I'm gonna go ahead and flip it. There we go. They are mirror images. Another check. Yay. No, they don't match up. Let's go ahead. Put one here and let's start rotating. No, maybe, no. Yeah, if this orange right here were red and this red right here were orange, then I think it could match up, but it's just not meant to be, Going, and we are almost back to where we started. No matter how much you rotate this molecule right here, it's never going to be this guy. They're never going to be the same. And that's it. That's all there is to chirality. Literally. Okay. So now let's start actually defining some of this other stuff. All right. So first up, we've got isomers. What are isomers? Same molecular formula, different compound. Okay. It's like, I don't know what that is. It's like we've got a C3H. Now I gotta think about this one. Or maybe let's make here. Let's do a C3H8O. All right. Well, let's draw it one way. We've got 1, 2, 3. Then we've got the O here attached to an H. That's one molecule. Then we got 1, 2, O here, and a carbon here. That's another molecule, and guess what? They both share this formula. How do I know? Because I Googled it beforehand. All right. So isomers. Go over the definition one more time. Same molecular formula. Different compounds. They are different. They've got the same formula. It's like two people with the same name, okay? No, they're not the same people. No, they're not clones. If they were, that would be really cool, but I highly doubt it. They are different people. Same name, different people. Same molecular formula, different compound. And these guys can split into two things. First one is one that we barely talked about, or not me, I guess. Teachers barely talked about it. So it's probably our favorite. Constitutional. All right. So constitutional, really simple, really nice. It'll become your favorite real fast. Same formula. Different connectivity. Okay. What does this mean? Well, let's say we've got a C4H something, because I'm not going to count them, so just put an X and a Cl. Well, one way you can draw them. Another way. Here, the Cl is connected on this second carbon right here. And here, the Cl is connected to this last carbon. Same formula, different connectivity. Same name, different way of writing it. I don't know how to explain it. It's just like take two, I guess, molecules, and if they look insanely different, chances are they're constitutional. Okay, like let's be real. Let's say you had like a easiest way I can think of this is a C6H whatever. 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. This or this. These two are constitutional, okay? They are constitutional. I don't know how on earth they're gonna look the same. They don't look the same. So same formula, different look. New year, new me. That's what this is. That's constitutional. Right? Now we're gonna go into something a bit more funky. It's the stereoisomers. Not gonna explain them fully. I'm just gonna like define them. I'll go over them in another video. Because there's multiple types of stereoisomers. Same formula, same connectivity, different arrangement. Okay. Wait, forgot to underline it. Same formula, same connectivity, different. You know what? Let's not call it arrangement. Let's call it Actually, arrangement's a pretty way of saying it. It's like how you place the stuff. Different way of placing the stuff. It's mostly rotating the stuff. Different way of rotating the stuff. And the stuff just happens to be bonds for the most part. Or breaking the stuff. Mostly. So, stereoisomers. We've got, for an example, we can have something like this. Or we can have something like this. These two are stereoisomers. Why? Well, let's draw them in 3D. So we've got a carbon chain here. We've got one that kind of sticks out like this. But the other one, it's got the same carbon chain, sticks out in the opposite direction. See, they've got the same connectivity. And both of these, this thing right here is sticking out on the exact same carbon. But the only difference is that it's sticking out in 2 different directions. Okay? So stereoisomers, same connectivity, same formula, just different way of putting the stuff. This time the stuff is sticking back, here the stuff is sticking front. Another way you can, another example of these is maybe the stereoisomers are not mirror images, and then you'll get pretty much the same idea. Which just will move us on to our next point. Point being, hopefully understand the stereoisomer, same formula, same connectivity, different way of rotating, placing the stuff. Anyways, there are 2 different types of them. We have enantiomers. Then we have diastereoisomers. No, diastereomers. Only difference between these 2 is that in enantiomers, they are mirror images. And guess what? They don't match up. You're not going to believe what they are. Enantiomers are really just chiral. They are just chiral molecules. Diastereomers are not chiral. They are not chiral. I repeat, diastereomers are not chiral. And do you know why? It's because they don't have this thing called mirror images. Diastereomers? No, not mirror images. So not mirror. No mirror. No mirror, no chiral. Okay? No mirror, no chiral. And they don't match up. All right? So we're going to go into enantiomers and diastereomers into another video. This is just an easy one, just running through what this stuff means. All right, take your photos because I'm going to erase this. And we're going to backtrack a bit to the fact that there are 2 different types of enantiomers and 2 different types of diastereomers. Thankfully, however, they are both called by the same thing: configuration or conformation. And it's actually pretty simple. Configuration, conformation. Configuration means that we've got 2 molecules and they can't become one another without breaking their bonds. So here, we must break bonds. Conformation, on the other hand, is that they can only become one another by rotating one bond. I think it's one bond. They say a single bond. So I don't know if it's a single bond or a single bond, like only one bond. So we're just going to go with rotating. Rotating a bond. All right. So the easiest way I can visualize this without putting any chemistry, like just so you guys can understand how this kind of works, is by involving breaking bones. So just trigger warning to any of you who do not like seeing headless people, headless stick figures in this case. I'm not going to draw anything fancy. Skip to whenever I'm done, or maybe just quit this video entirely. I will never know. Okay, so let's start with confirmation. We have our stick person. A confirmation of the stick person is the arm right here. And hold up, let me just hold up, switch the color. I'm gonna go for orange. In this case, the arm rotated. Well, that never happened. Rotated, yay, the arm rotates. That is a confirmation. Okay, sorry, yeah, confirmation. Arm rotated. Confirmation. Configuration is when you break stuff and attach it somewhere else. I'm gonna use his head because it's the most obvious part. So we're just gonna go with, yay, head is on his hands. This is a configuration. As you see, the head broke and is now attached to his arm. Breaking bonds, rotating bonds. Now let's go for a chemistry example. And maybe erase this. So good chemistry example. Maybe I should have Googled this beforehand. Kind of struggling to think of one. No, I guess the best way I can think of one is, let's say we have starting here. Let's start with a confirmation. Cl, just make this an F. And this here is our center. So for these guys, I think if we want to switch them, FCl, you could switch them by rotating the bond about this carbon center right here. So let me just draw that for you guys in a 3D. That make it a bit easier on me too. I mean, I'm not too sure what's going on. Probably should be though. So we've got our molecules. All right, so let's change the color of this. Now what we're gonna do, just gonna rotate them, okay? Rotate. I know that there's probably more stuff that's rotating, but for simplicity's sake. Yay, they rotated. See, they rotated that way. That would be a conformation, right? So now a configuration would be when the bonds break instead. So let's copy this over here. I guess instead, maybe you break this bond That would be attached over here. Yeah, the connectivity is different, but I guess I can find some better examples online later. Send in some homework questions you might have for determining if something is a configuration or a conformation. Or actually, you know what? Hold up. All right, so what we've got here is two models that I just built. And this first one here can have a conformation. It's going to help us understand conformation. And this one here is going to help us understand configuration because these are better than drawing. So let's go with it. So this one here, conformation. Let's hold this one over here, maybe, or let's just hold this red one here. What happens is that you have one side, it's going to rotate. We are rotating. We are creating different conformations because we are rotating. One conformation, another conformation. Wow, and there goes one more. And bam, it's the same one as before. You can even just like turn it around and make some more conformations. Just rotate them at the same time. Wow, so many conformations. Another one, very cool. All right, that's cool and all, but what about configurations? So configurations happen usually when you can't really rotate your bond. All right, and in this case, I guess the best way you can think about this is with cis and trans. Okay, so get your notepads out and write this one down. When you see something with cis and something with trans, they are configurations. And here's a little trick that we're going to learn later, but I'll just tell you guys now. When you see something with R and S, they are conformations, okay? Cis, trans, they are configurations. This guy. R and S, conformations. This guy. Rotating, remember? Conformations, rotating. R and S, okay? So this right here is cis. It's because these two guys, they are on the same side, okay? And this molecule can't really rotate. Can't rotate, see? Not gonna rotate. I'm probably gonna break this, but can't rotate. So in order for us to get another conformation, we need to break this bond right here. Wow, no way, we got ourselves a trans configuration. Yeah, not conformation. Okay, trans right here. The whatever is at the end, they're on different sides. Okay, they are trans. So just to recap, configuration, bond can't rotate anyway. So we're just gonna break it. Okay, cis, trans, configuration. All right. So that's it for today. If you guys have any questions, of course, comment below, or even like send me like, I don't know, homework you need help with. Might do another video. All right, don't forget to check out the website in the about section of the YouTube and click subscribe if you think this is remotely useful. Of course, I don't really expect it to be. Anyways, awkward goodbyes. Bye. Yay. Wow. Okay, have the pause recording.